Welcome to lecture 17. Today I'll talk about open systems, the Gibbs factor, and some examples of this. First, for a recapitulation. So some questions that in a normal lecture I would have waited for you to answer, but think about particles inside of a system that can be exchanged inside one box or between two boxes or between two systems. And how is the equilibrium characterized in terms of number of particles? Well, when it comes to number of particles, the equilibrium is characterized by the chemical potential being constant and the same everywhere. So if the temperature and pressure are constant and there is no external field, then the chemical potential is constant. So what do we then know about the concentration inside of a system or between systems? Well, if there is no external field, that means that the density of particles, that is the concentration or the number of particles per volume, is constant throughout the system. If the temperature and pressure are constant and there is an external field acting on the particles, so in equilibrium, what can we say about the chemical potential and the concentration? Well, we know that the total chemical potential has to be constant when there's an equilibrium. But because the total chemical potential is a sum of the internal chemical potential and the external chemical potential, then the concentration distribution will not be constant if there is an external field that's acting on a particle. So the concentration will not be constant in, for example, a centrifuge or in the battery that we used as an example last time. Or say in the concentration of oxygen molecules is not constant with height from here to Mount Everest. And this is the chemical potential is still the same everywhere, but because there is an external field, the concentration is not constant. Now, if the pressure is constant due to, for example, a semi-permeable if the pressure is not constant due to a semi-permeable membrane, how is the chemical potential and concentration in equilibrium? Well, the total chemical potential has to be constant in equilibrium, but the concentration will not be a constant if there is a pressure difference. And this is because one example of this is osmosis. So we see that the chemical potential is all about the equilibrium state, but what it affects is how number of particles or concentrations partition. And when the chemical potential is not constant, it drives a diffusive flux until the concentration has become constant or non-constant, well, whatever, that gives a constant chemical potential. So we could say that what's called the chemical potential, to us as a physicist, it's kind of a misnomer because it's got nothing to do with chemical reactions. Actually, it would be better to call it the diffusion potential or the number potential, because when it's the potential is not constant, it drives diffusion, and the equilibrium of this potential tells us how the number of particles per volume changes in the system. And I think that's useful for you to think about, that it's always about the number of particles, and this is the list I made last time, that it crops up in many different parts of the book and of our course. And here at the end, and we'll see next week that it also comes into quantum statistics, semiconductors, and so on. And today I'll go on to continue on open systems and the Gibbs factor. But first, a couple of comments on ensembles. So the word ensemble means a set of possible microstates that correspond to the macroscopic variables that are fixed. So far we've used the microcanonical ensemble, where the number of particles, volume, and internal energy is fixed. Then we've used the canonical ensemble, where the number of particles, volume, and temperature is fixed. And today I'll talk about the grand canonical ensemble, where the chemical potential, instead of the number of particles, volume, and temperature is fixed. So a bit more in detail, we remember in the microcanonical, it's the number of microstates we're counting, and which gives us the multiplicity omega, and the probability of a microstate is 1 over of a microstate is 1 over omega, and the entropy of this system is the Boltzmann constant times the logarithm of the multiplicity. In the canonical ensemble, we are studying a small system that is in equilibrium with a reservoir, and where it can exchange energy with the reservoir. And the reservoir itself is isolated, so the total system is a microcanonical system, but the system we're studying is a canonical ensemble, and because it can exchange energy with heat with the big reservoir, it means that the temperature is kept constant. The total energy does not need to be constant. And we've seen that for this system, it's the Boltzmann factor that's important, and we use the partition function to have a weighted sum of all possible microstates. And the probability of a microstate is the Boltzmann factor divided by the partition function. And then we got the free energy, which the Helmholtz free energy, which is the pertinent free energy for this system, which is minus kT times the logarithm of the partition function. So today I'll go in more detail and show you that the grand canonical ensemble, the chemical potential is kept constant, and this corresponds to having a small system in equilibrium with a large reservoir. The total system is microcanonical as before, but now the small system can exchange both heat and particles with the large reservoir. And because of this, the important factor is no longer the Boltzmann factor, but the Gibbs factor, where we've got the chemical potential and number of particles as well. And just like in the canonical ensemble, we now have the Gibbs sum instead of the partition function, which is sum over all the possible microstates with the sum over the Gibbs factors. And the probability of a microstate is the Gibbs factor divided by the Gibbs sum, exactly like in the canonical ensemble. And the free energy that's pertinent for this ensemble is what's called the grand potential, which is minus kT times the logarithm of the Gibbs sum. And this is the internal energy minus Ts minus mu n. So just to give you some idea of open system, what is an open system? For example, the crystal in a fluid, here the ions can pass in and out of the crystal, and they will flow in one or the other direction until there is an equilibrium between ions in the crystal and in the solution. The same for ions in the cells of our body. They will flow in and out of the cell and until and if there is equilibrium between the two sides, that the chemical potential is the same, then there will be no net flow. Also later we will go into looking at electrons or metals or semiconductors as our system and study how electrons are partitioned in bands and how these electrons can fill up different bands and how that makes something a conductor, a semiconductor, or an insulator.